there's two more topics I'm going to have to cover, and I only could do one and not the other. Okay, so the last topic is shaft design. I'll put on YouTube shaft design. It's not more difficult or what. It's just a procedure, and you guys can go look at it. But more important, the last topic that I'm going to cover for today, or for this course, is von Mises criteria. Yes. No. It's not fair where it's just 1 hour, right? So von Mises criteria. So this is based on distortion energy, okay, per unit volume. So the distortion occurs in the elastic region. So if you have an element, now all these are all in 3D, okay, like what we have in von Mises, everything's in on 3D. So this is X, Y, and Z. You have your element. And your element will have stress X, stress Y. Now, this is the theory, right? In real life, we know that 1 is equal to 0 or 2 can be equal to 0, okay? So based on distortion energy, he derived a formula, okay? So we are just going to apply. I'm not going to show you how is it derived. The formula that he derived shows that UD is equal to 1 over 6G bracket stress A squared minus stress A stress B plus by stress B squared. Okay. So I will define all this. So UD represent the distortion energy. Okay, so energy, so joules per meter cube. And then sigma A and sigma B, as you already know, they are the principal stresses. In 3D Mohs circle. And G is what we call modulus of rigidity. And you have seen this formula where shear is equal to G gamma, right? You've seen this before. And the modulus of rigidity is the same as when we use what? Stress is equal to normal stress is equal to Young's modulus multiplied by strain, okay? So alpha over gamma is the shear strain. Where over here epsilon is the normal strain. Okay, so this is theory. So what he did, what von Mises, now von Mises is a very bright character, okay? He uses energy which is different from Tresca. Tresca, what he did was what? Stress yield and just divide by what? 2. Okay, this is more advanced, okay? So he von Mises carry out uniaxial Okay, experimental. Okay, he carried out uniaxial experiment. So what he did, and all of you know this by now, what is uniaxial, right? Induce a tensile load, and then he put an element like what we usually do. So this is our x, this is our y, and this direction of z. Okay. So if we were to just look at y x direction, right? We have the element, or if we're going to, sorry, forget about the 2D. If we were to do this in 3D, right? So these are the hidden detail. We know there'll be a normal stress X. Okay. So now if we were to label all these surfaces, this is our X. Over here, this surface over here is our Z. And this surface over here is our Y. We finally, when we construct, we will construct a what? As you all know, we are going to get a mole circle. And it's possible to have a 3D mole circle represented by one circle. So we know that this is our point X. Over here, superimpose our point Y and point what? And point Z. So we also label this as our stress A. And over here, we can label it as our stress B. Remember what I told you earlier? Stress A and B are our principal stress. Okay. So based on experimental loading conditions, right? He realized, or we know that stress A is equal to stress U, right? And we also know that stress B is equal to 0, right? I will define stress capital Y. This is our U strength. And whenever you see a term U strength, this is from experiment. Like von Mises is the same, okay? Experiment. So from experiment, okay, he realized that U D to the yield is equal to 1 over 6G, right? And I'm going to write the first formula, the one that we written before. Stress A squared, stress A minus stress B plus by stress B squared. Okay. So the energy required to induce yielding, okay, so U dy is the energy required to induce yielding, right? So when that's the case, when we have U dy, this will be equal to 1 over 6G. We know that stress A is equal to stress U. So this is stress U squared. Okay, minus by stress U multiplied by 0 plus by 0 squared, because stress B is equal to what? 0. Okay. So this finally, the term that you get is you get stress U squared divided by 6G. Okay, this is what you get. Now, we are also aware, based on structure analysis, okay, so based on structural analysis, structure analysis means what you calculate, okay? Based on structure analysis, okay, the structure is safe when UD is less than UDU. Okay. So this UD is determined from structure analysis, means what we learn in this course. Whereas this term over here is the what? Is the mechanical property from material handbook. Okay. And some of you will say, I don't see that number at all. You are absolutely right. Don't see that number at all. So how do we apply this when we don't see the number? So we know based on this function over, or based on this expression over here, okay, based on this expression over here, right? We are aware that we have 1 over 6g square bracket stress A squared minus stress A stress B plus by stress B squared. This must be less than stress U squared divided by 6g. So we know, as I sound like a broken tape recorder, stress A and stress B are determined principal stresses. Determined from structure analysis. So we are aware that we can cancel this, cancel this. So all you need to know is stress A squared minus by stress A, stress B, normal stress, okay, stress B squared must be greater or must be smaller than stress U squared. Okay, so this is Vomisis criteria. Very different from what? Tresca, yes. Okay. So one thing that Vomisis assume the same like Tresca is Vomisis assume or also assume that the stress yield in compression is the same as tensile. So to apply Vomisis, okay, all you need to determine, as you already can see, are your stress A and your stress B, and your stress yield is from material handbook, okay? Now, if we were to look at this equation, before I go on by looking at this equation, you will ask ourselves, which criteria is less or more conservative? Right? When it's less conservative, you make more money. When it's more conservative, you make less money.